Now let's analyze the data we obtained from the Pathfinder. The manufacturer provides software to purchase to automate the analysis, but we're going to do it by hand in this case. I'm also going to use a mock example to simplify the analysis. After removing the paper grid from the Pathfinder or opening the photo, notice that the shade crosses several months within a gridded area. We're going to now count up those numbers that are within the shaded area of the grid by month. If we look at the wording on the arc of the Solar Pathfinder again, note it gives the word state shaded grid numbers give percent of total radiation for all south-facing surfaces. The numbers are listed in half-hour increments, so each number that is within the shaded area corresponds to a percentage of sunlight that is lost that month. In this case, for the month of December, we have 4, 5, 6, 7, 7, 8. That totals 37 or 37%. This means that 37% of the total light in December is lost on this array due to shading. Likewise, we can add up the numbers for January, October, November, and February, giving 37, 26, 36, and 32%. In general, if there's any area of shade in the summer months, you're almost always guaranteed to have shade in the winter months as well. The only exception would be an object like a vent or a chimney that might have some odd shade characteristics. We usually simply plan the array around those objects on the rooftop. The next step is to take the number of sun hours that are available and multiply them by the percent that's lost due to shading. You can get the sun hours using the NREL data tables or using another resource for monthly hours of sunlight, like within PV watts. It's important for this exercise to have monthly insolation values, not just the yearly average. The NREL tables give average daily hours of sunlight, so we need to first multiply the average daily hours by the number of days in the month. We then take that total and multiply by the percentage lost in each month given by the Pathfinder. The next step is to sum all of the hours lost due to shading and subtract the total annual insolation from that number. In this example, 37% of the sunlight hours are lost due to shade in the month of December. December has 31 days, so I multiply the sun hours in December, 2.1 kilowatt hours per square meter per day, by 31 days, and then multiply that by 0.37. That gives me a value for 24 full sun hours, or kilowatt hours, which are lost due to shading. If I follow that calculation through for all the individual months, then I have, of shading, I obtain 143.7 kilowatt hours lost due to shading. The location would normally receive 1,569.5 kilowatt hours per year. So I then subtract 143.7 kilowatt hours from 1,569.5 kilowatt hours per year, and I get the true annual insolation of 1,425.8 kilowatt hours per year. The last step would be to divide the true hours of insolation by the original annual hours of insolation to get the percentage of sunlight available during the year. In this case, it would be 90.8%, meaning 9.2% is lost due to shade. While any shading is bad, incentive derating tends to occur when energy lost due to shade exceeds 20%, although staying under 10% is preferred. There are other ways to calculate shade, one of them being using the software that's provided with the Solar Pathfinder. While that's more efficient from a time standpoint, it's an extra purchase, and if there are not a lot of arrays that you're designing, using the Solar Pathfinder tool and doing it manually may be sufficient. So in summary, the steps for shade analysis are to use the Solar Pathfinder and place it at the lowest 2 points of a roof for a rooftop system or on a proposed project area for a ground mount system. Obtain a photo or trace the area that's going to be shaded. Add the total hours lost due to shading for each month. Multiply the percentage of shade by the total kilowatt hours of sunlight per month and by the days in the month, and then subtract the hours lost due to shade from the annual kilowatt hours of insolation. If you're more advanced and doing a lot of solar designs, it may be advantageous to use an electronic tool such as the Solmetric Sun Eye. This electronic device takes a digital image of the sky using a fisheye lens to get that 180-degree hemispherical view. The advantage of the Sun Eye is that it will provide an immediate digital analysis of shading structures, but it does come with a cost. You can also you can insert or add or remove structures planning for the future to help answer that question, well, what would happen to solar access if we cut down a tree? Or what would happen if this tree grows 10 feet higher? Another advantage is that the system automatically corrects for azimuth and gives you an idea of what times of year are contributing to the majority of shading loss when not facing directly towards the equator. That's something that we have to do manually now. In the next segment, we'll compare the energy output predicted by a tool like PV Watts with the analysis provided by the Solar Pathfinder to calculate a more accurate photovoltaic electrical output.